My name is Parth, and I'm an engineer here at Arize, and I'm going to be hosting this paper reading session with Joe and Adam, and we're going to be talking about SEAL, and if guys want to kind of conceptually introduce what SEAL is, that'd be great.
Yeah, should I share my screen here?
Yeah, you can go for it, I think.
Nice. Okay. Um, can you see it?
Yeah, I can see it.
Okay, great. So yeah, I'll just go over the high level motivation here. Um,
Hmm.
let's hit the play button. Sorry. Okay, so stepping back, so we have been using these impressive language models. And an interesting thing to think about is their weights are static as we're using them, right? And I think this brings up the question, should our neural networks always be static in inference time, right?
Hmm.
And I mean, that's up to debate, but I think probably not. And I think two pieces of evidences are, one is our brain. We know we have neuroplasticity. Our brain does change over time, although it does slow down as we age, but still, it still keeps structurally changing. And also, we know just purely doing in-context learning has limits as well, whether this be like efficiency limits or capability limits. So stepping back, if we want a model to be deployed in the wild, and we're looking for like the next frontier of intelligent language models, it'll need to adapt itself and likely adapt its weights in two key scenarios. One is when the external world, the environment it's been placed in, whether that's humans, other agents, or just like even the physical world, provide you some signal. And this is what our work focuses on. And the second is when the model itself, if it thinks about a question for a long enough time and it has like a epiphany or an aha moment. And this is something that it wants to maybe like inject back in its own weights as a persistent knowledge update. These are like broadly scenarios when we want the weights of a model to actually change after it's being deployed. And if you look at prior work, I want to make sure that it's clear we're not the first people to propose the idea of self-adapting neural networks. Even Schmidhuber has had works in the 90s called like self-referential networks that in the high level do this. Um, However, other works that try to adapt these models, one is they sometimes require other specialized like helper modules, whether that's like regulate the objective function or hyper network style like um, output weights. Um, and we already know our current language models and our current transformers are quite powerful. So the question is, can we somehow utilize their existing capabilities with outputting tokens and different chain of thought and leverage that to actually generate a weight update? So the question becomes, can we somehow parameterize weight update using tokens? And I think that was the key motivation for this project, such that now we can let models think about a problem or see some new signal from the environment, think about it for some time in just like the normal chain of thought, but then also in token space, somehow output a sequence of tokens that cause and trigger and parameterize a weight update.
Yeah.
Um, yeah, Adam, you want to say something?
Yeah, so we call these self-edits, these parameterizations of weight updates. And we have found and we believe that the best way to do this is through generating synthetic data for itself to be trained on. And this is the way that um, all language models are trained. They see data and they do next token prediction on that data. So a language model can generate these tokens, and a language model can learn from these tokens the best way to parameterize weight update is just through generating this data. Now we have these two kind of ways that we go about doing this. One is through literally like rewriting a document or writing some implications of this document. And another is doing some tool calls for synthetic data generation. And we'll get into both of these later. So I think everything up to this point has kind of been thought about before. Different works have done, like taking some document and trying to use it in context to generate more data for itself. Our paper introduces the idea of using reinforcement learning to train this ability to self-edit. And here we have a kind of a form of meta-learning where there is an inner loop in which the model is being trained on data that is generated, and then an outer loop in which we're training the model how to generate the data that trains itself on. So yeah, this double loop makes this an instance of meta-learning. And
we'll talk about we'll walk through the
yeah.
exact method just to make it super clear. I
Yeah.
think something that's pretty cool, just like stepping back to like more general audience, it's quite interesting that we're able to train the model such that the parameters themselves know what they should do to like change themselves. And I think that was kind of something I found very interesting. Like, how do you get these weights that know what they should do to like, edit themselves? I think that's just a cool phenomenon in general.
Yeah. But again, it is just another task, the task of generating synthetic data, which means we can do this reinforcement learning loop on it. And we have this sort of clever reward of we can generate like many candidate self-edits. We just apply all of them and see which updated model has the best downstream performance. And this is the reward for our reinforcement learning loop. It's the downstream evaluation of the updated model on questions relating to the data that was adopted.
Yeah, we can go to the next slide, and Adam, you can explain like the steps in the knowledge incorporation setup. I'll step through the slides. So like first the context.
Yeah, sure. So yeah, I think this is going to be more concrete. Let's say we have this document on the left, like it's just a passage about the Apollo program. We want to learn from this document and inject it into its weights, model's weights. One way of doing this is we just train on the document, do your standard next token prediction on all of the tokens. However, this doesn't work very well. Since it's a single passage, there's people have found just training on a small amount of data from this information presented in a single way really does not work as well as having it in context. So that's why we do this self-edit generation, where the model generates augmentations of this data, basically long lists of ways of rewriting this data, restructuring of the data such that it can hopefully be ingested better by the model. And you can kind of think of this analogous as to like a student taking notes after reading some content. They can kind of restructure it in a way such that it's easier to digest. So here we have 3 candidate self-edits, and this is showing our reinforcement learning loop. This is the meta learning aspect of things. We're generating multiple self-edits and evaluating each of them, and from this evaluation, we basically can determine which is the best self-edit and use that to train the model to produce better self-edits.
Yeah, Um, and just to like make it clear, like, so Adam mentioned the inner loop, outer loop optimization. So in this animated slide, that one, the chunk you see everything to the left of the evaluation bar, like this is our inner loop optimization, where we have parameterized our weight update using this self-edit, this yellow SE box. Each one causes, after you do like SFT or some other optimization, you get this new updated weights denoted by the prime sharp hash. Each separate model now is then evaluated, and we can test how well it was adapted with some downstream tasks. And finally, this whole outer loop is now, we train the policy on just how well, like which self-edit generated the best adapted model. So the action space here is just on the self-edits. So in the bottom right, you can see like the RL box. It's important to note here that it's atypical for the model's weights to be considered this as the state in the typical like RL formulation. However, in our situation, the reward you get depends on the current model theta t, because even if you take different self-edit actions, like you have different weight parameterizations you're outputting, since they're ultimately added to the current their model's weights, different base model weights with the same applied self-edit will cause different adapted models and thus different rewards. So although we don't explicitly input the model's own weights into itself to generate a self-edit, it's implicitly there because it's like the model's own weights. But I think this is just like kind of like a interesting caveat.
It's just a subtle point about
Yeah.
our RL setup.
Yeah. If it's a bit confusing, I mean, maybe it's not a huge deal. It's just like something interesting to point out. I guess we can move on to the next setting. So for those who are not familiar, ARC is this visual puzzle. It was aimed at testing like reasoning capabilities. There is an underlying rule that takes a grid of colors and transforms them. And given a few examples, you want to figure out what's the underlying rule. Prior work, also from MIT, has shown that doing test time training can often outperform doing in-context learning. So what that means is I give you these few examples. So let's say I have these few shot examples here, where the blue image is the input, and the greener version is the output. So the underlying transformation, this simple case, is just you just take the colors and you turn from blue to make them green. The actual tasks are harder than this. It's just for illustration. And given these few shot examples, you need to figure out, okay, what is the underlying rule? Now, for these like harder versions of this task, like just putting them in context to the model is often not sufficient. And what prior work has shown is you take these few shot examples, you do many synthetic augmentations to it to generate more data, more XY examples with the same underlying transformation. And you train the model on these synthetically generated data. And then the updated model is better answering or better understanding what is that underlying transformation, is able to answer or output correctly the prediction for unseen inputs. So in our formulation, what we did is we took the same setup that people use for test time training here, and instead of the design decisions that the researchers had to manually hand tune, we decided, can we just use our formulation to have the model output the right like synthetic data generation configurations and the optimization configurations. So to walk through the setup here, These few shot examples go into the model. And here, the self-edit becomes which augmentation tools do you want to call? So this is like binary true or falses. Each one is going to take these few shot examples, synthetically apply the set of augmentations to generate more examples. And also it's going to output optimization configurations. So learning rate, epochs, and also which type of tokens do you want to take the loss on? Just in all the tokens or just the output tokens? So the synthetically generated data, highlighted with the blue box, plus the optimization parameters are all used to do supervised fine-tuning. We then get the updated model. And in this figure, just because of space reasons on the slide, I'm only showing you one sampled self-edit, but similar to the previous knowledge incorporation setup where Adam walked through the 3 different sampled self-edits and how each one gets a reward. We also sample 15 different self-edits because we're doing reinforcement learning. Now we test with the updated model theta prime, we show an unseen input and we evaluate, did it predict it correctly? And similarly, we use this to do meta RL. So I guess this is a good stopping point since we kind of did impart a decent amount of information. If like there's any questions on the methodology itself,
yeah, no, could you go back a slide
yeah,
to answer Sebastian's questions?
yeah.
So first, how do you know what the correct output of the eval is?
Oh, oops, sorry. Wait, sorry. Okay.
Yeah,
Just go to eval. Yeah.
Yeah, so the idea in this setting, which I should have mentioned more clearly earlier, is when you have this context, or when you have this passage in your context window, the language model has good understanding. It can answer these questions. Like if you ask the GPT-4, you give it the context and you ask who is Kennedy's science advisor, blah, blah, blah. It'll get it right 100% of the time. But the goal is to kind of learn from the data such that we can answer questions without the data in context. So, so for evaluation, similarly, when you have the data in context, you can easily just determine whether the answer is right or not. So you can use the same model or GPT grading, and yeah, it's usually pretty clear. And then the point of the time steps. So are you referring to like the 1, 2, and 3 on this slide? If so, these aren't really time steps, they're reinforcement learning candidates. So often in reinforcement learning, you generate a number of possible actions, which in this case are self-edit generations, and then you reward the one that does best.
Gotcha. So, I mean, there's a lot of ways to rewrite like this context. So, what did you guys see? What did you guys see in like simple terms, like what worked and what didn't? Like what
Well,
types of text?
yeah, the most obvious was longer is better,
Mhm.
which makes sense when you're doing synthetic data generation. Like you want to see the same information in many different ways.
Mhm.
So yeah, RL would prioritize longer sequences. And
Gotcha.
then there may be some slightly more subtle things involving, like the formatting and the kind of um, like diversity of the ways things are presented.
Right.
This we're less confident about, but ideally, you want to kind of present the same information in many diverse ways and kind of have implications that are not present in the text. And this is kind of a possibility, but yeah.
But as appellation, we did try just like what happens if you prompt it with generate a longer sequence. And across the prompts, we see like reinforcement learning does improve performance. So it is like an interesting question because we don't know exactly how the model is like what is the right like the underlying thing that is making the rewrites helpful. But I think that's like a very interesting thing to also figure out.
Got it. Okay. And another question I had after reading your guys' paper is if there were, I mean, like you guys saw catastrophic forgetting as a phenomenon, and I hope, I mean, I was wondering if you could kind of just briefly touch upon that. Really, yeah.
Yeah,
Yeah.
I think so. We have that in the, let me just go through the slides now.
Sure.
Yeah, that was overview. Okay, so results. I don't know how interesting it is to like stare at the results.
Mm,
I do want to make it clear because I know there was like some false information on Twitter. Like we used a simplified subset of ARC. This is not the full set just because we used a smaller model. So that's why I put this. I just want to have the disclaimer.
mhm,
Uh, and then yeah, we can see that on the top row, each iteration of RL1, 2 um, improves the performance. And we do use a few steps of RL, like to a normal RL person, if you say, oh, I did 2 iterations of RL, they would be like kind of surprised. It's just in our case, each RL update takes a while because we're actually doing supervised fine tuning in each step of RL because we have the 2 loops, so it's just quite expensive.
mhm.
Also, iterations here refers to a batch of 50 training examples. So you can think of it more as 50 and 100. And every example is variance reduced using 3 generations.
Got
Yeah,
it.
and
So read the
yeah,
paper for
for
details.
academic compute, like I think that's why it was few, but I think the main thing is we just showed like good signs of life of this idea. And to your catastrophic forgetting question, yeah, so that is a current limitation, and that's what I'm actually currently working on to try to mitigate. But pretty much what we see is like there is gradient interference happening. So um, since our self-edit parameterizes a weight update, um, it specifically we generate a LoRa, and okay, we add this LoRa back into the model. We see a new input. We generate a new self-edit that generates a new LoRa, which gets added back. But if these like LoRa's are say like operating on the same subspace and like they're going to interfere with each other, it starts to cancel out and overwrite the previous things you learned.
Mhm,
So yeah, what I'm trying to do is like have the model have more control with the actual weight update itself and try to make it such that these updates can be made in a way that actually reduce interference, but that's ongoing work. So um, yeah, and it does make this paper like not immediately uh, usable in a continual fashion. Um, uh, but yeah, things
Yeah.
it's still important. It's an interesting limitation. Yeah.
Yeah.
Okay,
There's
gotcha.
one question in the Zoom chat about kind of computational inefficiencies. Um, and yes, so during reinforcement learning, each iteration does take a while since we have to do this intermediate training step. We use LoRa adapters, so it works out to around 45 seconds per like single iteration of RL, which is not too bad, especially since um, in practice we would not really deploy like the model would not be doing reinforcement learning on the fly. It would be doing training on the fly, right? So after the idea is like the RL is kind of a warm up such that the model knows how to self-edit effectively, and from there, um, there's a number of things you can do involving test time training or kind of sleep wake cycles where you have like um, like every day uh, you have the aggregate of all of the self edits that are generated, and then you apply all of them at once. So yeah, there's a few different ways um, that you can do the updates after
Yeah.
doing that.
Um, and I guess we can go through the future direction. So I think beyond trying to improve, Adam just mentioned the computational part, which is true. I think so beyond just trying to improve the computational efficiency of our method, I think there are some more high level directions that are worth considering. So one is that I mentioned in the beginning, there are like broadly two settings where we'd want to update the model's weights. One is when the environment provides you an external signal, but one is actually when your model itself, say like mid-reasoning, realizes something that maybe should be imbued in its weights as a persistent improvement. So I think if people kind of can leverage our work and combine it with like reasoning training, like using reinforcement learning for training, just like regular like reasoning, if a model has some key aha moment, it could be interesting that if actually doing a weight update to really understand that aha moment actually improves the rest of the chain of thought reasoning, I think that'd be good. And another thing would be instead of just having one model, we're just like thinking about a setting where one model is training itself. I think in the future, it's likely that we're going to have multiple agents all interacting with each other. And in such a paradigm, we can think about similar to how humans oftentimes learn from each other through collaboration. These self-edits could be used to actually parameterize the weight update for another model. So models can actually just be teaching themselves as like a society of continuous learners. And Adam, maybe you can talk about the pre-training corpora one.
Yeah. So actually, I'll first answer a question from Matt in chat, and then I'll go along with this. So in figure 5, it looks like the second iteration rewrite is longer than the input context. Do you see any signs of hallucination? Yes, we do not quantify hallucination since this kind of requires either like human graders or like taking a stronger model and trying to figure out which parts are actually following from the context. However, in general, I think as we scale things up, it'll look like the rewrites are going to be a lot longer than the original passage. So often in real world data, there's kind of not enough information to understand every single token. For example, if you're reading a dense academic paper, maybe there's a lot more that can be said. And you can imagine a model essentially writing blog posts for itself in response to this academic paper, explaining every single detail. The aggregated data is going to be much larger than the original. And if you have a strong enough model, then this is going to really enhance the base capability. Hallucination is, of course, an issue, and it's yeah, somehow we're gonna have to figure that out to like have really robust ways of doing this. But even with hallucination, you can kind of see how scaling this up could yield like really big improvements.
Yeah. Oh,
so yeah, this goes along with pre-training. Like we experimented with a single model adapting itself on the fly. It's also possible to kind of have two models or like a single teacher model and a student model where this teacher model is generating data for the student model, whether it's pre-training or post-training data. Yeah, if you imagine like augmenting an entire pre-training corpus, maybe you can get better pre-training results.
Yeah, and something I want to that I think is quite interesting, I've been thinking about is we know we haven't seen many signs of curriculum learning being that useful in like say pre-training. I mean, there is like a data mixture that people use in pre-training where at the final end people go to like very high quality sources, but there isn't like the level of pre-training where I first ask a model to learn like say easy math problems and medium math problems and like harder math problems. Like in pre-training, this data is like kind of like jumbled up, and models may see like calculus immediately, then algebra after. So, but I think something that could be interesting in this rewriting the pre-training corpora would be if you have a model, let's say, like starts with knowing basic algebra or basic math, and then it now sees like a harder math topic, it could actually think about that math topic for a while and actually rewrite it in terms that it already knows. So for example, it could like rewrite the calculus in like terms of like algebra that it already knows. And in this way, you could actually have models creating their own like curriculum for themselves during pre-training by being able to break down something that can be actually re-represented with their current knowledge. So I think people can also like investigate that direction of how to improve pre-training. That could also be quite interesting. And I think that was the last slides actually. So
Yeah. Thank you guys so much for your brief introduction to your research. I think the aha moment, that future direction is particularly most interesting to me. Thank you guys, and thank you guys in the audience for the awesome questions. And yeah, I think we're over time. But if you have any additional questions, please visit the Slack channel. Yeah, thank you so much, Joe and Adam, one more time, and
yep.
see you guys later. All right,
Thank you.
Thank you.
see ya.